Have you ever wondered why some objects float in water while others sink? It's not magic, it's science. Specifically, it's all about buoyancy and Archimedes' Principle. These fundamental physics principles explain why your rubber ducky stays afloat during bath time, and why that stone you threw into the lake sank straight to the bottom. This journey into the world of fluid mechanics is sure to make a splash. Imagine you're floating in a swimming pool. Ever thought about the forces at work? Enter the buoyant force, a physics principle that's working its magic every time you take a dip. But what exactly is it? In the simplest terms, buoyant force is that upward push you feel when you're in a body of water, be it a pool, a lake, or even a bathtub. It's the force that keeps you from sinking straight to the bottom. But don't be fooled. This force isn't only at play when you're splashing around in water. It's present in any fluid, including the air around us. It's just that its effects are more noticeable in denser fluids like water. So, where does this force come from? It's all about pressure. Fluids exert pressure in all directions. But here's the catch. The pressure is greater at deeper points because there's more fluid above pushing down. So, when an object is submerged, the fluid pushes harder from below than from above, resulting in an upward net force, our friend, the buoyant force. Now you might be wondering, does this mean all objects in a fluid experience buoyant force? Absolutely. Regardless of their shape, size, or weight, all objects immersed in a fluid feel this upward push. But here's where it gets interesting. The buoyant force working against gravity is what determines whether an object floats or sinks. If the buoyant force is greater than the object's weight, it floats. If it's less, the object sinks. And what about those objects that neither float nor sink, but stay suspended in the fluid? Well, in that case, the buoyant force and the object's weight are perfectly balanced. So the next time you're bobbing in the pool, remember it's the buoyant force that's keeping you afloat. It's a fundamental law of physics that's silently at work, whether we're aware of it or not. Now that you understand buoyant force, let's delve into Archimedes' Principle. Opening. Ever heard of the Greek scientist Archimedes and his famous principle? Well, let's dive into it. Archimedes' Principle is a fundamental law in fluid mechanics that helps us understand how objects behave when immersed in fluids. It's a concept that might seem tricky at first, but it's actually quite simple when you break it down. Imagine you're at the pool and you decide to take a plunge. The moment you're in the water, you feel a certain push, an upward force that's trying to bring you back to the surface. That's the buoyant force at work, and it's all thanks to Archimedes' Principle. This principle states that the upward buoyant force experienced by an object immersed in a fluid, whether fully or partially, is equal to the weight of the fluid that the object displaces. In simpler terms, if you throw a stone into a pond, the water level rises. That rise in water level is the fluid displaced by the stone. The upward force that the stone experiences is equal to the weight of that displaced water. But how does this determine whether an object will sink or float? Well, it all depends on the relationship between the weight of the object and the weight of the displaced fluid. If the object is heavier than the fluid it displaces, it will sink. If it's lighter, it will float. And if the weights are equal, the object will neither sink nor float, but stay suspended in the fluid. Think about a ship. It's made of steel, which is much denser than water. So, how does it manage to float? Here's where our friend Archimedes comes in. A ship displaces a large volume of water, which weighs more than the ship itself. Hence, the buoyant force is greater than the ship's weight, and it floats. So, buoyant force and Archimedes' Principle are the secrets behind the floating or sinking of objects in water. Next time you're in a pool or watching a ship sail by, you'll know exactly what's going on beneath the surface. Wondering where you'd ever use these concepts in real life? Well, ponder no more, as we dive into the various applications of buoyant force and Archimedes' Principle in our everyday world. Let's start with the high seas. Ever marveled at the sight of a massive ship floating effortlessly on water? That's Archimedes' Principle at work. When designing ships and submarines, engineers use this principle to calculate how much water will be displaced by the vessel. This helps them ensure that the buoyant force equals the weight of the ship, allowing it to float. The same principle applies to submarines. By adjusting the volume of water in their ballast tanks, they can control the amount of water displaced and hence their buoyancy, allowing them to dive or ascend at will. Now, let's take a leap from the ocean to the sky. Have you ever watched a parachutist gracefully descend from the sky? That's another application of buoyant force. When a parachutist jumps from an airplane, the upward buoyant force of the air opposes the downward force of gravity. By manipulating the size of their parachute, they can control their descent speed, ensuring a soft landing. Similarly, the buoyant force also plays a crucial role in the movement of fish in water. By changing their body volume, fish can regulate their buoyancy and move up or down the water column. Archimedes' principle also has a significant role in the realm of density measurement. Let's say you have a fluid and you want to know its density. By observing the buoyant force required to displace a known volume of the fluid, you can calculate its density. This is particularly useful in industries where the density of substances needs to be accurately measured, like in oil and gas, food and beverage, or pharmaceutical industries. Finally, let's talk about something that might sound a bit abstract: determining the volume of displaced fluid. You might wonder, why would I ever need to do that? Well, imagine you have an irregularly shaped object, and you need to know its volume. Instead of struggling with complicated mathematical formulas, you can simply submerge the object in a fluid and measure the volume of the fluid displaced. This gives you the volume of the object thanks to Archimedes' principle. So, as you can see, these principles are not just confined to the pages of a physics textbook. They are essential in many fields, from engineering to marine science. Whether it's designing a ship that can withstand the weight of thousands of tons, understanding how a fish swims, or even measuring the density of a fluid, Archimedes' principle and the concept of buoyant force have a significant role to play. These principles are essential in many fields, from engineering to marine science. Let's recap what we've learned today. We've embarked on a journey into the world of fluid mechanics, exploring two fundamental laws: the buoyant force and Archimedes' principle. We've discovered that the buoyant force is a result of fluid pressure, which pushes upwards on any object immersed in it. It's this force that opposes the gravitational pull on the object, determining whether it sinks, floats, or remains neutrally buoyant. We've also unpacked Archimedes' principle, the ancient Greek scientist's invaluable contribution to physics. This principle states that the upward buoyant force experienced by an object submerged in a fluid is equal to the weight of the fluid displaced by the object. The beauty of this principle lies in its universal application, regardless of the shape, size, or type of the object. But we didn't stop at understanding these principles in theory. We delved into their practical applications, showing how they're woven into the fabric of our everyday life and engineering marvels. We saw how Archimedes' principle aids in determining the volume of irregular objects, simply by measuring the volume of displaced fluid when these objects are submerged. This principle also plays a pivotal role in designing ships and submarines. By understanding buoyancy, engineers can create vessels that can float and support their weight, ensuring safe and efficient maritime travel. We also explored the role of buoyant force in analyzing the motion of objects in fluids. From the graceful swimming of a fish to the adrenaline-pumping fall of a parachutist, the buoyant force helps predict how objects will behave in various fluids. And lastly, we saw how the buoyant force can be used to measure the density of fluids. By observing the force required to displace a known volume of fluid, we can calculate the density of the fluid, a principle that has numerous applications in science and engineering. These laws of physics, while seemingly complex, are at play in our everyday life. They help us understand and predict the world around us, making the unknown known and the complex simple. Next time you see an object floating or sinking in water, you'll know exactly why that happens. Thanks for tuning in.